Here's something most people aren't talking about. SpaceX might have been overthinking the moon mission this whole time. Right now, the plan involves launching multiple tanker starships. We're talking potentially a dozen or more flights, just to fill up a fuel depot in orbit. Each of those tankers has to survive the brutal journey back through Earth's atmosphere, protected by thousands of heat shield tiles, complex guidance systems, and landing hardware. All that reusability comes at a price. Added weight, added complexity, and added risk with every single launch. But there's another way, a simpler way that SpaceX used to do with Falcon 9 before they mastered landing boosters. What if they just didn't bring Starship back? Strip away the heat shield, remove the landing flaps, eliminate the header tanks. Suddenly, you've got a rocket that can carry up to 250 metric tons to orbit. That's more than 3 Skylabs in a single launch. The International Space Station weighs about 420 tons. An expendable Starship could deliver that entire mass in just 2 flights. Now, before you say, wait, isn't that wasteful? Here's where it gets interesting. Without all that re-entry hardware, each Starship becomes cheaper to build, and you save all the propellant normally reserved for landing burns and recovery. Most importantly, you dramatically reduce the number of refueling flights needed to get to the moon. Fewer launches means fewer chances for something to go wrong, faster mission timelines, less complexity, and potentially the edge NASA needs to beat China back to the lunar surface. Of course, this raises some serious questions. Is throwing away multi-million-dollar spacecraft really more practical than perfecting reusability? What does this mean for SpaceX's long-term vision? And why hasn't this option been seriously discussed until now? Welcome to Space Update 24 Hours, where we break down the space stories that matter. Today we're exploring the expendable Starship option, a strategy that could reshape the entire Artemis program and fundamentally change how we think about getting back to the moon. Let's dive right in. When Starship screams back through Earth's atmosphere at 17,000 miles per hour, 12 times faster than a speeding bullet, it's fighting physics in the most brutal way possible. The energy that needs to be shed during re-entry doesn't just increase with speed, it multiplies by the square of that speed. A small bump in velocity triggers a massive explosion of heat. The spacecraft's surface glows white hot, pushing into temperatures that would vaporize most metals in seconds. To survive that inferno, Starship needs thousands of thermal protection tiles covering its entire body. But those tiles are just the beginning. The reusable version demands header tanks filled with landing fuel, massive aerodynamic flaps for atmospheric control, redundant sensors monitoring every critical system, complex plumbing networks, and sophisticated software that has to work perfectly every single time. Each component adds weight. Each system introduces another potential failure point. Now here's where it gets interesting. What if SpaceX just didn't do any of that? Strip away the flaps, trash the heat shield tiles, delete the header tanks, simplify the guidance system down to basics. You're left with something radically different, an expendable Starship that's lighter, simpler, and frankly easier to build. This isn't about abandoning reusability forever. SpaceX can still recover the Super Heavy booster, which carries the most expensive Raptor engines and represents the biggest chunk of hardware cost, the upper stage. Let it complete its mission and burn up on re-entry or drift away in deep space. If SpaceX had started with a simple, expendable upper stage, they could have been launching serious payloads to orbit years ago, then perfected the reusable version on their own schedule. Instead, they went all in on full reusability from day one. Every test flight has been about nailing that belly flop maneuver, those final moments when Starship flips vertical and fires its engines to land. It's spectacular when it works, but it's also incredibly hard to pull off. This strategy matters even more when you're talking about the moon. NASA's current Artemis architecture using Starship is complicated. SpaceX launches a depot version of Starship into low Earth orbit. Then they launch a parade of tanker Starships, each one docking with the depot and transferring propellant. Once the depot is topped off, the lunar lander version launches, refuels from that depot, and heads toward the moon. It meets the Orion crew capsule in lunar orbit, ferries astronauts down to the surface, then brings them back up. The big question? How many tanker flights does it take to fill that depot? Estimates are all over the map. Some say 8, others say 15. The honest answer is nobody knows until Starship reaches operational maturity with proven propellant transfer efficiency. But everyone agrees on one thing. It's a lot of launches. Every launch carries risk. No matter how reliable your systems become, spaceflight never reaches 100% certainty. A tiny O-ring can doom a shuttle. A helium valve can strand a capsule. The more times you light those engines and send hardware screaming toward orbit, the higher your cumulative risk becomes. Expendable tankers change the math entirely. According to SpaceX's own performance figures, an expendable Starship can haul up to 250 metric tons to low Earth orbit. To put that in perspective, Skylab, America's first space station, massed about 76 tons. A single expendable Starship could launch 3 Skylabs worth of hardware in one shot. The entire International Space Station weighs roughly 420 tons. Starship could theoretically orbit that entire mass in just 2 expendable flights. Throwing away a Starship every time sounds wasteful until you run the numbers. The expendable version doesn't carry grid fins, doesn't need thousands of heat shield tiles, and skips all the complex re-entry hardware manufacturing costs drop significantly. But there's another advantage, propellant savings. A reusable Starship has to save fuel for re-entry burns, landing burns, and the entire recovery operation. An expendable version burns every drop getting payload to orbit or pushing toward deep space destinations. Some engineers have pushed this concept further with drop tank designs. External fuel tanks feed propellant into Starship during major engine burns, then get jettisoned once they're empty. The physics are straightforward. Acceleration pushes fuel toward the engines, so you don't need complicated pump systems. These disposable tanks would let Starship carry even more fuel without sacrificing payload capacity. The real advantage shows up when you factor in the Oberth effect. When you burn rocket fuel, you gain more energy by firing your engines while you're moving really fast, particularly at the lowest point in your orbit near a planet. The same amount of fuel burned at high speed delivers much more energy than burning it slowly in a higher orbit. Sometimes it actually makes sense to dip deeper into a gravity well, just to burn fuel at maximum velocity. An expendable Starship loaded with drop tanks could take full advantage of this effect. It could reach the moon with fewer refueling flights in Earth orbit. It could perform high-energy burns that would drain the tanks of a reusable version, trying to save fuel for landing. For early Artemis missions racing against China's lunar ambitions, this approach offers a faster, more straightforward path. Drop tanks come with their own challenges, though. Large external tanks create structural issues when you're pulling multiple Gs during ascent. If they drain unevenly, you get thrust asymmetry that makes the whole stack wobble. Releasing them mid-burn is risky and bleeds away some performance benefit. Operating in higher orbits for extended periods also exposes your spacecraft to more orbital debris. Every hour spent above the atmosphere is another hour when a paint chip traveling at orbital velocity could punch through your propellant tanks. The uncomfortable truth is that outside of lunar missions, almost nobody needs this kind of lift capacity right now. That's why Falcon Heavy, despite being the most powerful operational rocket today, flies maybe 3 or 4 times per year. When you're operating a fully reusable system where the marginal cost is mostly propellant, it makes more sense to launch smaller payloads more frequently. What missions would actually justify expendable Starship's full 250-ton capacity? Massive space station modules, next-generation space telescopes that dwarf James Webb Heavy Surveillance satellites. These missions exist, but they're rare, and even when they do, fitting something that weighs 150 tons into Starship's cargo bay is difficult because internal volume becomes the limiting factor, not mass. Skylab proves this point. At 76 tons, it was the heaviest single-piece satellite ever launched. It was also far too large and awkwardly shaped to fit inside Starship's current fairing. Any organization designing a spacecraft that heavy would probably be better off making it modular, launching it in pieces and assembling it in orbit. If that rare mission ever materializes, SpaceX can simply grab a Starship off the production line, skip installing the heat shield tiles, and fly it expendably. There's no reason to prepare for this scenario years in advance. They can wait for the customer to show up with a contract in hand. For NASA's Artemis program, Expendable starships represent a bridge strategy. They let you lift more mass, burn more aggressively, and reduce refueling complexity. All critical when you're racing to beat China back to the lunar surface. You pay for that capability with higher hardware costs and a less elegant long-term architecture. But when the clock is ticking and political pressure is mounting, fast beats elegant every time. While everyone debates reusability philosophy, the European Space Agency just shipped the Artemis 4 service module to Kennedy Space Center. 6 months ago, that hardware almost became a museum piece. The Trump administration's 2026 budget proposal called for ending Orion and SLS after Artemis 3, canceling Gateway entirely, and handing everything to commercial systems. Artemis 4 survived only because Senator Ted Cruz pushed through a last-minute funding restoration in July. $41.1 billion for SLS missions and $20 million for new Orion capsules. That European service module suddenly had a purpose again. It'll power the 2028 mission that delivers the IHAB habitation module to Gateway, building permanent infrastructure in lunar orbit. Here's the real message. Expendable Starship isn't about abandoning reusability. It's about having options when the mission demands them. For routine operations, full reusability wins on economics every time. But for early Artemis missions where China's building their own lunar lander, where every refueling flight compounds risk, where political wins can erase programs overnight, Expendable offers speed. SpaceX won't maintain separate production lines. They'll keep refining reusable starships, perfecting heat shields, nailing those landings. But when NASA needs heavy Gateway modules delivered before the next budget battle, they can strip the tiles, load the payload, and fly. The race back to the moon isn't just about elegant engineering. It's about American boots on lunar regolith before competitors arrive. Sometimes a shortcut wins the race, and that's not compromise, it's strategy. Should SpaceX prioritize speed over pure reusability for Artemis, or commit to the fully reusable vision, regardless of timeline? Drop your take in the comments. If this breakdown delivered value, smash that like button and share it with anyone tracking the new space race. Want every SpaceX development and NASA decision as it happens? Subscribe to Space Update 24 hours and hit notifications. The next few years will redefine spaceflight, and we're covering every move.